Hello, 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 my organic chemistry class. I love it. Let's do some OChem. I am putting together a series of videos for cycloalkanes. This is our first video in that series, so we're going to actually have more than one. So this is just the first video in this series. This first video, our focus is going to be vocab. Let's just get to know our general class of cycloalkanes. You guessed it, that is alkanes in a ring. These exist in nature, some more common than others. We can also make them in the lab. So we'll see these throughout the entire semester of OChem. We'll see rings quite a bit. In fact, like I said, they are in nature. We've got rings in all kinds of things, from our sugars to our amino acids to our steroids. They're quite abundant. So I want to start with this video as basic vocab. Let's get to know our cycloalkanes. Let's get to know a couple major topics, and that is going to be isomers, ring strain, and symmetry. So this first video will apply this vocab for the rest of the semester, but I want all this vocab just in one place. So because we're going zero textbook, like I had mentioned before, here's a bunch of links for our cycloalkanes just to get you started. And this document, I would love for you to hit pause for a second and grab this document from Blackboard. It's going to have all of these links. I'm also trying something new, and I'm embedding some videos in here. So you're going to have links, pictures, videos, everything in here. In this series of videos for cycloalkanes. Okay, awesome. So you kind of guessed it. If we were normally talking about alkanes, let's start with one of our favorite alkanes, propane. And let's write out their molecular formula. We've been learning a lot about our formula for alkanes. We follow that general structure of CN, H2N plus 2. And then let's compare that to, could we have propane but actually connected to itself in a ring? Yeah, we can. The difference is this is now called cyclo, propane. And then what is our formula? So I want to challenge you. Are these isomers? Remember, our first rule of isomers is the same molecular formula. So in our propane, we've got 8 hydrogens. How many hydrogens do we have in our cyclopropane? Only 6. So indeed, these are not isomers. And for every ring you have in your formula, you'll notice we subtract 2 hydrogens. So this is now just 2N. And if we actually get to some fused bicyclics, which we will in our roadmaps, then just remember that for every ring, you're going to subtract 2 hydrogens. So your formula could be changing. In fact, that's awesome in a roadmap because you can then start with the formula and figure out if you have any rings. So they are not isomers, even though they both have 3 carbons. They are both propanes, but our cyclo has minus 2 hydrogens. I love it. All right, there's another even bigger difference with our cyclos. We're going to start with cyclopropane, and then we'll work our way up through all the rest of these ring sizes. But our cyclopropane, I would love for you to pause for a second and grab your model set. Let's model this. If we start to model, we're going to notice right away when you put your model set together, and here's our little backbone, here's our 3 carbons in our ring. We're going to notice, first of all, that that's actually hard to put together. That is hard to assemble. What you're literally feeling is something called ring strain. This is our first topic with our cycloalkanes. We're going to hit some vocab here. When you literally try to connect those atoms It actually feels like you're going to break the model set. And what's happening there is we're feeling this ring strain. And you guessed it, that ring strain takes energy. Our ring strain is actually not just one thing, but it's actually 3 general strains all the way up through cyclohexane, and then there's a 4th strain when we get bigger than cyclohexane. We're going to focus on the first 3 strains. The first one you're feeling when you're trying to assemble that model set is called angle strain. Remember, we're dealing with all carbon and hydrogens, all single bonds. And what then is our perfect shape in space, sp3, tetrahedral? And why do we care about tetrahedral? With tetrahedral, everything is evenly spaced. And that angle is 109.5. We know from our Newman Projections video that really you need to picture bonds and atoms as big balls of negative in space. And if they're getting close to each other, they repel, and that takes energy to actually force those groups close in space. They're repelling each other. They're big clouds of negative. So anytime you get away from that 109.5, that is going to take energy. That is our first strain. That is our angle strain. The farther you get away from 109.5, the higher the strain. So let's take a look at our cyclopropane. This is what you felt when you tried to put that together. That angle is actually 60 degrees. That is quite far away from angle strain. Now, is that strain so high that you don't see these ever? No, but they're actually somewhat rare. You've got to work at having a cyclopropane because of that strain energy. They're not super common. All right. And then number 2, we're not actually done. I want you to take your model set and start to turn it. I want to start to picture almost like a Newman projection where we can start to look down these bonds. And that's going to help us with our second strain called torsional strain. So I've got that down here. If you could take your model set and literally picture that Newman projection. Holy cow, look at all of our hydrogens. And in fact, if we turn it, you're going to see it lines up completely everywhere. And that's, we learned this in our last video. Isn't this incredible? Look at this. If I were to picture a nice, I just paused for a second there. If I were to picture an actual Newman projection, oh my gosh, look at that. Wouldn't I have to draw everything all in a line? Well, what kind of Newman projection is that? Completely eclipsed. This is our second strain. This is called torsional strain. This is literally eclipsed bonds. And in the case of our cyclopropane, holy crap, they are all eclipsed. So if we were literally just on our last video, we would know and recognize that this is our worst energy conformation. But I know what you're thinking. You're thinking, Dr. Morty, just chill for a second. These bond rotate. Well, grab your model set and try to turn a bond. They are fixed. Especially in that cyclopropane, your bond rotation is restricted. Literally, you'd break bonds if you try to rotate those. And so you're kind of trapped in this eclipsed conformation. And we know that takes energy. That definitely takes energy. And then our third is called steric strain. Now on our Newman projections, we saw these with gauche. So anything bigger than hydrogen, we're going to look at steric strain. So for just cyclopropane, we've got these first two, angle strain and torsional strain, and they are big. So again, do these exist in nature? Sure. Are they very common? No. They've got a lot of that strain, and in fact, they can spring open again. Now we're going to take a minute when we hit our other two topics to also look at steric strain. So for each one of our cyclos, we're going to consider all three of these strains, and we're going to look at that energy. So in order to start looking at steric strain, we have to start putting something bigger than hydrogen on our cyclopropane. So for our next two definitions, I'm going to challenge you, so you may want to hit pause for a second. Let's make dimethyl cyclopropane. And then we're going to hit isomers, steric strain, and symmetry. It's going to be awesome. All right, so I want to also work my way through some of our drawing. Our first drawing method for all of our attachments is this nice skeletal drawing called line bond or kekuli. We are always going to start here. This literally just shows attachment. And this is our first kind of isomer. So if we're challenged to make dimethyl cyclopropane, let's see what we've got. Well, we could put both methyls on the same carbon, or we could put methyls on two different carbons. Now these are awesome. This drawing is the best for seeing this type of isomer. I'm going to give us a little table. Our isomers table, all isomers have the same formula. Now we're going to get deeper. What we're looking at are constitutional. Okay? That is literally atom attachment. They are attached different. So these two examples right here, these are constitutional isomers. We also saw this with our butane and our methylpropane. These are constitutional isomers. And then in our last video, we learned a new isomer, conformational. These are a bond rotation. So we saw those in something like butane, where we considered our best and our worst energy conformation. Awesome. Okay. So these are conformational isomers. We will see those with our cyclos as well. And then third, we have something called a configurational isomer, and those are arrangement in space. All right, now the reason I like to spread these out right here and define them is that our three different drawings are for our three different isomers. We start with our skeletal. That is going to point out, wow, we actually have two different compounds. That tells us nothing about a bond rotation or a 3D arrangement in space. Conformational, we have to use either a Newman projection, or we're going to learn in our next series of videos something called the chair. We have a very specific way to draw this because we're looking at the energy of where stuff is in space. So these two methyls being next to each other, that is going to take energy. Our Newman projection shows that. It'll be the same with our chair. So we're going to need to draw a different way. We've already done this one. This one is coming up next. Okay. And then third, when we look at a configurational isomer, that is our arrangement in space. This is where we're going to use bolds and dashes in order to show that arrangement in space. So let's focus on this one right now. But go ahead and keep this table. We'll keep adding to it over this unit and the next unit. So let's take our constitutional isomers and let's show you what a configurational isomer is. So if I take this cyclopropane, I can actually have two different arrangements in space. So let's take this and expand it. What if we take our cyclopropane and one of those methyls is up and one is down? Or what if they're both up or both down? So we have to use bolds and dashes in our drawing to actually tell our audience where in space are these things. And I've got them drawn in just a second underneath here, but I can also draw them from the side. So let's imagine they look like this. Those would be on the same side. What if we draw this like this and say, okay, wait a second, what about that? Okay, now they're on opposite sides. So this is our third kind of isomer. You still have two methyls on there. They're on the same carbon. They're just a different arrangement in space. These are configurational isomers. Let's go back to our table for a second and let's add that this drawing correlates to our table. So let's talk name. Okay, these are going to have a completely different name. These are going to have the exact same name because they're the same thing. And what happens to a configurational isomer? We're going to add to our name. So in this case, we're going to add cis out front of our dimethyl. Cyclopropane. And in this case, we're going to add trans out front. Not a comma. So our configurational will always be out front of the name. All right, so in the rest of the semester and in the rest of our series here of videos, we're actually going to see all three of these types of isomers: constitutional, conformational, and configurational. I love it. We're also going to see three different ways to draw them. We're going to always start with that skeletal structure, and then we're going to add to it if we have to consider energy at all. We're going to draw either Newman projections or chairs. And then as soon as we want to look at that arrangement in space and figure out if we have configurational isomers, we are going to use those bolds and dashes. So for the rest of this video series, we're going to use all three methods to draw. And we're going to get good at drawing those. All right, so we're also going to add then one last topic, and then we're just going to draw. So I want to add a little bit more vocab between our two cyclopropanes. And this vocab is going to help us in our later unit. So I've got both, I've got both the cis and the trans for our cyclopropane here. We've got our cis, and we've got our trans. Let me draw that better. Okay, we've got our cis and we've got our trans. And you can see our two methyl groups here and here. These are on the same side, so that's cis. And then you can see in this one, our methyl groups are on opposite sides. That is trans. Okay, these are our two configurational isomers. We're going to add to our vocab just one more term that we cannot tell unless we're using those bolds and dashes. One of the most common mistakes in OChem 1 is to show me symmetry without drawing in 3D. You have to have this configuration in order to figure out what your symmetry is. So take a second, pause, and model these. Your cyclopropane, we've got two options for that methyl group here. It can be up or down in relation to this methyl group. So we have something called symmetry. In fact, in chemistry and in nature, there's at least 7 different symmetry operators. You'll hit those in inorganic chemistry. I want to hit the 2 most common operators of symmetry. The first one is called a plane of symmetry. And this is going to help us in our later unit in stereocenters, chirality and optical activity, because if we have a plane of symmetry, we will not see optical activity. A plane of symmetry is when you literally can put a mirror right down the middle of your structure, and you have literally what looks like the mirror image on both sides. It looks like you've got, this half looks exactly like this half. So it's sometimes called a mirror plane or a plane of symmetry. And you'll often just draw a line where that mirror would be. They're literally the same side. It would be like holding a mirror up right here. Okay, then what about trans? We actually don't have that. If you picture a mirror, this is missing. So this does not have a plane of symmetry, but yet there's something about it that's actually quite symmetrical. This is the harder one to see. This is called C2 symmetry. Now that is not carbon 2, this is circle divided by 2 symmetry. That means 180 degrees. If you take a circle and divide it by 2, that is 180 degree rotation. So what a C2 symmetry means is you can rotate your molecule 180 degrees. So in this case, we could literally rotate this molecule 180 degrees, and you would get the exact same configuration in space. So if you can rotate 180 degrees and you literally look the same, that is C2 symmetry. So that is really hard to show on drawing. So what I've done is embedded a video. Now I don't know that the video will pop up here on my iPad. I don't see a little play. So this is one of those places you want to stop and go to the Word document that I've posted for you and click play on that video. I do a 180 rotation of that molecule so you can see that C2 symmetry. And that 180 rotation could be kind of flipping like a pancake, like you're going to flip a pancake, or it could be spinning and rotating like a top. Doesn't matter how you rotate 180, it just matters that you rotate 180 degrees. All right, so now we've hit our 3 topics. I do want to add steric strain to this, and we're done with our vocab. So it's easiest if I draw it on here. So I want to go ahead and add in there, I'm going to add to our ring strain that number 3, and that was steric strain. So now that we've got stuff on our cycloalkane, let's compare the cis and the trans. Look at these 2 methyl groups on the cis versus the trans. If we're looking at this methyl group right here and here, They are awful close in space. That is steric strain. If we look at our trans, and we do that same thing, let's highlight methyl over here, methyl over here. They are nowhere near in space, so there is no steric strain there. So in fact, if I were to just ask you, what's your gut tell you, which one is going to have lower energy and be more stable, you would probably guess trans in this case, because you don't have that number 3 ring strain, which is steric strain. Okay, I love it. Let's take this. I just want you to have a million links. So this document again is posted on your Blackboard. So for all of this ring strain, isomers, ring strain, and symmetry, we've got a bunch of links for you to read. If you've, again, of course, if you've got any organic text, you're going to have a nice chapter that hits all of this stuff. So that's cool. And then what I want to do is go ahead and practice a little bit on these rings, and then we'll stop this video and we'll come back to our rings. So let's go ahead and practice. Okay, so we've got a nice skeletal drawing here of our cyclobutane. We are going to have all 3 ring strains as soon as we get to here. We will have angle, right? Because we are at a 90-degree angle, nowhere near our tetrahedral. We will have torsional. I would love for you to build that model set, and you're going to notice that these are eclipsed. I think I even turned, I did not. I did that for symmetry. And then as soon as we start to add some methyls, we will have a steric strain. So in fact, our cyclobutanes are quite rare. They are quite rare in nature. They have that special strain that actually, if you tend to heat them a little bit, they blow up. So they tend to be not so abundant in nature. But let's go ahead and add some of our vocab. Okay, so right away, what are our isomers here? These are constitutional. These are configurational. And then let's go ahead and add our symmetry. So in this one, oh, can't I draw a nice mirror plane right down the middle? This has a plane of symmetry. Okay, what about this one? This nice trans, if you flip that like a pancake, you get the same configuration. This is C2 symmetric. Okay, now here's the trippy one. What about this third one? You actually have a plane right there, and you can flip. It is okay to have both. So in fact, you have both a plane of symmetry and C2 symmetry. This is a good place to pause, build your model set, and double check that you can see some of that symmetry. Okay, then what's your guess tell you down here? We've got a nice plane of symmetry here. And then what about here? C2 symmetry. Now I included some of our model sets just to help you. So if you want to pause and build your model set, here is our cis. And look at this. I can picture a mirror right there. That has a plane of symmetry. You can also then picture, if we were to look at this one, oh, it just got real in here. We have a C2 and a plane. Look at that. If we turn this one this way, we actually have both. We have C2 and a plane. Okay, symmetry is a little bit tricky. It's easiest when you look on a model set and then you get used to it and you can tell from these drawings. Isn't that fun? Let's do one more set. I'm actually going to leave it up on the screen and let you try it. Just remember our type of drawings and isomers. So again, these are constitutional. And then within these, we have to include bolds and dashes. These are now configurational. And how about here? Configurational. So then have fun and try your symmetry on these. And I'm going to end this video, and then we're going to work our way into just cyclohexane.